Okay, hello everyone, and welcome back to Physics 3150. Last time we continued our discussions on sequential circuits, and we talked about different examples of the sequential circuits and where flip-flops, different kind of flip-flops, D flip-flop and T flip-flop, could actually become useful. We saw counters, different kind of counters, and we talked about resetting the counters and detecting a certain number at the end of counting process. And in the end, we talked about an example where we wanted to use an adder to build a counter, and we talked about the importance of flip-flops as the gatekeepers to actually incorporate timing into the structure of that adder. So to generalize that idea, um, so basically, let's write it here. So physics 3150, and this is March 24th, 2020. Okay, so the idea was that I had a counter, I had an adder. Basically, I wanted to build to make a counter, so I had an adder. I took the output of this adder and I said, well, for a counter, I just want to add the previous number by 1. So it's just basically connect the previous number to the input of the adder, and the other input of the adder is just 1. And to kind of add timing to this thing, I'm going to connect flip-flops in between. This basically the previous number, the output of the adder goes to the D input of the flip-flop, and the Q is going to be the output that goes to the input of the adder. And this basically is controlled by a certain clock that is shared between all these flip-flops. So for details, go back to the notes of the previous lecture. So let's generalize this situation, generalize this kind of structure. We can say that I always have this current state, which I'm going to show it with Y, and I'm going to have next state. Let's call that Y prime, or some people use a star or asterisk. Doesn't matter, just something else, right? I've seen people using Y asterisk, people using capital Y. You can use whatever you want, just different from the current state. And I'm definitely going to have some input into this system. We're going to talk about that input and how is it going to come into the picture. So I'm going to call that W, and I'm going to have some output. So I'm going to say it's called Z. Now I'm going to build my system around my flip-flops because those are the most important blocks in my system. So let's say I have a bunch of flip-flops. We're going to go with D flip-flop for the simplicity, but you can make it with any kind of flip-flop. And they all share the same clock. Okay. And what I do is that I would say the output of this flip-flop is kind of the current state, right? And this current state could be a multi-bit current state. For example, the current state in the counter case was basically the numbers, right? So we're counting up, and it's a 3-bit counter. So let's say this is bit 0, this is bit 1, this is bit 2. So I'm going to call it a 3-bit state. So let's say that this is Y1, this is Y2, because we decided to actually show the current state with Y, right? And then I always have the next state, which is going to be valid, which is going to be current state after the positive edge of the clock, right? Once the clock comes in, the next state becomes comes to the output of the flip-flop and becomes the current state, right? So the next state should be actually here. So let's show it here. So y1 prime, y2 prime, and y. Well, this is really put 3 dots here so that to show that this is could be multi-bit. So this is yn, and this would be y prime n. Okay. Now I could have some output. For example, in the counter case, let's say that my output, I want this counter, I want to count, and then what I'm really interested in is to get a output of 1 whenever I have reached the number 5, which is, well, 5 is a 101. So when this is 1 and this is 0 and this is 1, I want to get a 1. So just AND all of these together. And that would be my output. I'm going to call it Z. So basically there's always, and this is the simplest output generator, but this could be a very complicated combinational logic. And by combinational, I mean the first basic, the basic type of logic gates that we talked about, the first part of the digital logic circuit part of the course that we have been discussing. So this could be a combinational block, and out of this we're going to have our output, right? And now how do the next state is actually created? Well, if you think about it, we had another combinational block here. So what we had here as the combinational block was really the adder, right? And what was the input of the adder? Well, it could have been some inputs. In this case, it was just a 001. Could be like if I wanted to count up basically the odd numbers, it would have been 002. Or like if I wanted to count up by multiplications of 5, then it would have been a 101. But there is always some input. And when I show this W and this Z at the output, I don't mean that they're one bit. They could be multi-input, multi-output. We could have a system with multi-input and multi-output. So, and we're going to see examples of that. So don't worry about that. But just to mention that it doesn't mean that it's a single input, single bit input. But then the other important input to this combinational block, which was our adder in the example that we saw, is really the current state, right? The current state makes the next state, right? So what we need to do is to actually bring, I'm going to use a different color. We need to actually bring these guys and connect them to the input of the combinational block. This way, I can use my current state, which is y1, y2, and yn. In this case, it was basically the current number that we have in the counter, and then feed it to the combinational block, and the inputs are coming from here, and then I'm going to create the next state, right? So the next state is going to be basically created from this combinational block. I'm going to call it y1 prime, y2 prime, and yn prime. And this next state is going to be here ready for me to become the present state once the clock cycle, like the positive edge of the clock, comes into the picture. Okay, so for the counter example that had an adder, we really didn't have a step-by-step design kind of procedure. What we did was basically we kind of designed in an arbitrary way, and it started working, and like basically we were successful. But then what if we actually have to design a system that needs both sequential and combinational logic, and basically we need to have a procedure to actually design such systems? For example, when we wanted to design any kind of combinational logic, what we did was our procedure was basically we started with truth tables, and then we converted truth tables to Carnot maps, and then we converted Carnot maps into sum of product Boolean expressions, which we could implement using AND gates and OR gates, right? So we'd like to have some kind of a step-by-step procedural kind of a way for these systems as well, right? So as an example, remember the USB port we talked about? So imagine that you want to design an algorithm inside your processor, and what you need to do is that you want to actually find the pattern in the bits that are coming in, right? So for the USB, we talked about the fact that the bits are coming in serially. You get one bit at a time, right? Let's say the bits that are coming in this direction is basically, let's say 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, something like this, right? And then here's your processor, so microprocessor, and basically it's kind of like it's looking at this thing from this point, and the bits are coming in this direction, right? And let's say we want to detect a 101, meaning that if I receive a 1 and a 0 and then a 1, I want my processor to generate basically like raise the flag, says that I have detected the pattern that you liked, right? So initially when I'm looking at this, the first bit that I see is a 1, then a 0, then a 1, and then so my flag goes up, right? But then the next bit that comes in is a 0, so initially I was actually looking at the 101, then I'm looking at a 010, so the flag goes down, then I'm looking at again a 101, so the flag goes up, then 110, 111, 111, 011. You can see that for none of these basically packages of 3 bits, bundles of 3 bits, the flag, for all of them, the flag stays down, right? Until I guess I get to the end where I get another 101, right? So the bits are actually coming in one at a time, and I'm looking at the last 3 bits, right? So basically the last 3 bits, or the newest, by last I mean the newest, the most recent 3 bits that has arrived in microprocessor, and I want to see if I see a 101 kind of a thing, right? It's kind of like basically the same idea of you're in a production line, and they're telling you that we want to actually detect this pattern whenever you saw, for example, the product that is green and then a red and then a green. Well, stop the production. That's a faulty kind of story, right? Or like you're waiting in an airport and you're there to basically you're waiting for someone you haven't met yet, but then they text you and they tell you that I'm the guy with eyeglasses, and in front of me is a guy with a green jacket, and in front of him is another guy with eyeglasses. So let's say eyeglasses is 1, green jacket is 0, eyeglasses is 1. So you're looking for a 101 kind of a detector. So you wait there until you see that pattern, right? So to detect such a thing, if you want to actually design a process, like inside your processor, if you want to design an algorithm to detect such a thing, we need to have something that is called state diagram. So basically, initially, let's say that you start with a state, we're going to call it 0, 0, 0. Let's say that I have the last 3 bits that I have received is 0, 0, 0, right? If the next bit is actually a 1, so let's say if the input to my system is a 1, I'm going to go to the state 1, 0, 0. And I'm using 3 bits 0, 0, 0 or 1, 0, 0 because I'm looking at the last 3 bits, right? So let's say I was in in a state that had 3 zeros, and I got a 1. Now it's a 1, 0, 0. Still, the output is actually 0. What if I get another 1? Well, I throw out the most right bit and bring in another 1. So I'm gonna go to the state of 1, 1, 0. Still, the output is 0, or meaning that the flag is down. What if I get another 1? Well, I go to state of 1, 1, 1. And what if I get another one here? Well, if I get another one, I'm throwing out this one and I'm bringing in another one here to the left, right? So this means that I still gonna have a 1, 1, 1. So if I get another one, I'm just gonna stay here, right? I'm gonna be basically imagine that you're waiting for your friend who you haven't met yet, and you have seen 3 guys with green jacket. So you're in the basically state of 1, 1, 1, and then if you get another guy with green jacket, still the last 3 people that you've seen are with green jacket, none of them with glasses, so you're in the state of 1, 1, 1, right? Now, what if I get a 0 at this point? Well, I go to a state that is basically 0, 1, 1. Okay, let's say I get another one. I go to 1, 0, 1. So you get, I'm hoping that everybody gets the idea. Whenever an input comes in, that input becomes the most left bit, and then the most right bit of the previous state just goes out. We throw that out. Now, if I get another 0, I'm going to go to 0, 1, 0. W is 0. And then if I get another 0, I'm going to go to 0, 0, 1. Okay, but then you might think that, well, initially when you were here at 0, 0, 0, when you got a 1, you might have got a 0, right? So what would happen if you get a 0 here? Well, I would stay here, right? If I had 3 guys with eyeglasses coming, basically arriving at the door, if the 4th guy also basically has an eyeglasses, then still the last 3 persons that you've seen had eyeglasses. They're all zeros. So W is equal to 0. Now, looking at the second state, again, we have to kind of like basically consider all the possibilities. We consider the possibility of if W is 1, but if W is 0, what will happen is that I go from a 1, 0, 0 to a 0, 1, 0, which I have it here. So basically, if W is 0, I'm going to be going to this state. Okay, now for the third one here, if W is 1, we know that we go to a 1, 1, 1, but if W is 0, we're going to go to a 0, 1, 1, right? So 0, 1, 1 is really here. If W is equal to 0. Now, for the 1, 1, 1, we consider W being 1 or 0, so nothing is really left to actually consider. For 0, 1, 1, we said if W is equal to 1, we're going to 1, 0, 1, but if W is 0, we're going to go to 0, 0, 1, which is here. Next, for 1, 0, 1, if W is 0, we know where we go. If it's 1, we go to 1, 1, 0, which is here. So this is if W is equal to 1. And then for 0, 1, 0, if W is equal to 0, I'm going to 0, 0, 1. If it's 1, I'm going to 1, 0, 1, which is, right on top. Okay. And then for the last one, if it's basically, we haven't actually considered any of this situation. So if I get a 0 here, I'm going to go all the way back to the first state because I'm going to throw out the 1 and I'm going to bring it 0 to the left. I'm going to get a 0, 0, 0. If I get a 1 here, I'm going to get a 1, 0, 0. So if I get a 1, I go here. If I get a 0, I go there. Okay. So why did I drew this state diagram? It's kind of like basically it summarizes all the things that could happen, right? So I have 8 different states because the 3-bit number can have 8 different possible values. So 8 states because a 3-bit number can have or can take 8 different values. And then for each state, I know that from this state to the next state, it's a serial port. So I'm going to get 1 bit at a time. At every moment, at the positive edge of clock cycle, let's say, 1 bit at the right is going to be thrown out, and 1 bit to the left is going to be added, right? So that bit that is coming in could have could be either 0 or 1, could only have 2 different values, right? So I considered all those possibilities for all the 8 states. For each state, I looked at what will happen, where do I go, which state do I go if W is 1, and which state do I go if W is 0, right? So based on this, I could actually summarize the entire possibilities that could happen to my system, and well, nothing else is gonna happen, right? Basically, nothing different, nothing other than these states and transitions that I've shown could ever happen. Now, when does my output become 1? Well, here. So in this state, z is equal to 1, right? So the moment, it's not really a transition, so maybe I should actually write it here, z is equal to 1. The moment you're in this state, the flag goes up. In any other situation, the flag stays down. Now the question is, well, yeah, this is a good way of actually describing what is happening in the system, but then how do you want to implement this using the gates that we have learned by up to now, right? So it's kind of like, basically, yeah, you drew the flow chart, but then how you're going to actually implement it using the syntax and using actual code. That's what we're going to discuss in the next slide. Okay, now let's convert the presentation that we had in the previous slide, the presentation of the system that we had in the form of a state diagram, into something that I would like to call state table or transition table. So we know that the state table is going to look like this. So I know that I have something that is called current state, and because my states are 3 bits, from 0, 0, 0 to all the way to 1, 1, 1, my current state is going to be a 3-bit number, and we decided that we're going to show the state with y. So I'm going to write this from 0, 0, 0 all the way to 1, 1, 1. And then I'm going to have next state. But then for the next state, it's not only, we saw that it's not only a function of the current state, it's also a function of the input, right? So if W is equal to 0 or W is equal to 1, I'm going to have different states, right? So I'm going to look at my state diagram in the previous slide and then decide what should be the next state. So let's call this next state y2 prime, y1 prime, and y0 prime. So the next state is going to be basically, for example, if I have a 0, 0, 0 and I get a 0, I look at my diagram, it tells me that I stay in the same state, so I'm going to get a 0, 0, 0. If I get a 1, I look at my diagram and I see that I go to 1, 0, 0. So looking at the diagram, I can actually fill out these states one by one. So I'm going to get a 0, 0, 1, a 0, 0, 1, a 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1. And then on the other side, I'm going to get 1, 0, 1. If I get a 1, if I get a 1 here, it's again 1, 0, 1, 1, 1, 0, 1, 1, 0, and 1, 1, 1, 1, 1, 1. How about the output? That's the last part of my table. So the output is kind of like the flag, right? It only becomes 1, we said, if the current state, not the next state, the current state is 1, 0, 1, right? So it's going to be 1 here, and it's going to be 0 for all other states. Okay? Now, the way I'm going to basically designing this whole thing is basically similar to the structure that we've talked about. So the way I'm going to build this is I'm going to say, well, my state is actually a 3-bit state. So I'm going to need 3 flip-flops. These are D flip-flops. And I'm going to have a clock here connected to all of them. And basically their output is going to be Y2, Y1, Y0, right? Now, the input to this flip-flop, show it with a different color, is Y2 prime, Y1 prime, and Y0 prime. And the question is, how do I actually generate this Y1 prime, Y2 prime, and Y0 prime using the previous or the current state? So like basically if I bring in this guy and this guy and this guy, and I know that I'm going to need a W as the input, I need to have some combinational logic here that generates the next state from the previous state. And I have some basically information here that will in this table that is going to help me, right? As for the output, it's actually quite easy in this case. So the output is basically, it becomes 1 when you have a 1, 0, 1. So you get a 1. For the second one, it's whenever it's 0, so a bubble. And for the third one, just the Y. You do AND gate of all of them, and that's going to be your Z, right? So whenever you get a 1, 0, 1 as the current state, Z is going to be 1. Otherwise, in any other kind of any other 3-bit number is going to give you a 0. So the question is right now is that how do I generate this Y2 prime, 1, 1, Y1 prime, and Y0 prime? If I can generate these guys, then I'm done, right? I've made my system that uses both combinational and sequential logic, right? Now to do this, I know that I'm gonna basically approach this in a 1-by-1 kind of a way. So I'm gonna start with Y2 prime, right? So Y2 prime is the most significant bit of the 3-bit number that is representing my next state. Remember when I had this table, I had, like, for example, 0, 0, 0, 0, 0, 1, and then here I had 0, 0, 0, 1, 0, 0 from the previous slide, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, and then 1, 0, 1, 1, 0, 1, and so on and so forth, right? So this is the next state. So this is really for W equal to 0, W is equal to 1, right? What I'm going to do, let's write these as well. Okay, so what I'm going to do is only to look at for Y2 prime, I'm going to only look at the most significant bit here and the most significant bit here, right? It's going to give me 16 different numbers. Why 16? Because I have 3 bits for my current state, Y2, Y1, Y0, and I have 1 bit for the input. So I have 4 bits, so I can get 16 different cases. Or like I have 3 bits for a state, so 8 different cases. And then each of these 8 cases could be like for W equal to 0 or W equal to 1. So I get in total, I'm going to get 16 different cases, right? So now looking at this, I'm going to say that, okay, so I have a Y2, a Y1, a Y0, and a W. The combination of these 4 is going to give me Y2 prime. And I'm going to do the similar thing for Y1 prime and Y0 prime. So how do I actually do this? Well, from this point, like from this perspective, I'm really dealing with the combinational logic design. So I can do whatever I did with the Carnot maps in the past. I can say that, let's imagine a Carnot map. I'm going to go 4-by-4 because I have 4 inputs, Y2, Y1, Y0, and W, right? So let's say up here, I'm going to have W, Y2, and here y1, y0, and I want to actually figure out what would be the value of y2 prime. Okay, so looking at this, and I'm going to fill this out the same way that I do for a normal Carnot map. So 0, 0, 0, 1, 1, 1, and 1, 0. Now, looking at this, I can see that basically for when w is 0 and y2, y1, y0 are 0, I'm looking at this cell, and in this cell I have basically this is the cell, and here is the equivalent number, like the equivalent of that cell in this table, right? So which tells me that y2 prime should be 0. Again, for example, this cell, if you want to think about it, it's a cell that I have a state 1, 0, 0. So 1, 0, 0. And basically, if you look at the table that we had in the previous slide, we got 0, 1, 0 and 1, 1, 0. 0, 1, 0 and 1, 1, 0 for this, right? So you can see that for this state, when w is 0, we have the cell that I'm showing in red here, right? And that is represented by this bit, okay? So I'm gonna get a 0. So I'm gonna translate this table, or like I'm gonna basically convert the information that are presented in this table into a Carnot map. So I'm gonna fill out this Carnot map with this table. So all I need to do is to look at only this and this column, right? So I'm gonna get 0, 0, 0, 0, 0, 0, and actually 1, 1, 1, 1, 1, 1. Okay, so looking at this Carnot map, it's actually one of the best Carnot maps that we could get, because you know that you can easily do this, circle around all the ones, and say that y2 prime is really equal to w, right? And thinking about it intuitively, it does make sense. Remember that when we had a bunch of 3 bits, or when we had the bits coming in one by one, the most left bit was always the input that was coming in, right? We threw out the most right bit, and then we replaced the most left. We shifted everything to the right, and then the most left bit was actually filled with the input. And well, this guy is actually saying exactly the same thing in a different way, right? In a Boolean algebra way. Okay, so now if I continue and basically build this for y1 prime, so this is one of those moments in the video that I really encourage you guys to pause the video and do this for yourself, and then once you were done, you can actually resume the video and then check if you did it right or wrong. Okay, so please pause the video right now, try to actually do the table for y1 prime and even y0 prime, and then continue and see if you did it correctly or not. Okay, so if I want to do this myself, the table, if I basically, for this case, I'm going to be looking at these bits, because those are the y1 primes for w equal to 0 and w equal to 1 for different states, and I'm going to get basically, again, a very nice Carnot map. If I draw a circle around it, I'm going to get y1 prime is really equal to y2. And if I do the same thing for y0 prime, so very similarly, you will get y0 prime equal to y1. Okay. Now, how do I make this circuit? how do I complete my circuit? So it's basically, I had this D flip-flop, Q, D, Q, D, Q, and these were the clocks. And looking at the output, well, the output was basically, we did it before, so this was Z. And now I know that the input goes simply to Y prime 2 or Y2 prime, so this is W. So remember, this is Y2, this is Y2 prime, this is Y1 prime, and this is Y1. This is Y0, and this is Y0 prime. So now I know that Y1 prime is equal to Y2, so I'm just going to connect them. So Y1 prime should be connected to Y2, and Y0 prime is equal to Y1. And that's it. My circuit is completed. So I'm showing these big dots to show the connection. Okay, so this is how I make my circuit, and this is the clock. It has a sequential part, which is the heart of the system, the D flip-flops, the area of D flip-flops. The output of flip-flops are the current state, the input of the flip-flops are the next state, and then in this situation, we really have the combinational circuit that converts the current state to the next state is actually quite simple. We saw that the expression is actually very simple. That's why I really didn't need to have a huge combinational circuit generating the next state. But you can imagine that these Carnot maps could actually result in a very complicated kind of expression of sums of products. So you can imagine that you might actually end up with having a bunch of ands and ors, right? Another way of looking at this circuit, if you think about it, we really designed a shift register, right? So I can actually draw this. If I call this one, let's use a different color. Let's call this one flip-flop 1, 2, and 3. I can really draw this in this way. This being 1, this being 2, this being 3. And what is really happening is that W is coming in, the output of this one goes to the next one, the output of this one goes to the next one, and the output of the last one, well, we really don't care about it. We throw it out because we threw out the most right bit, right? And then we took these three, inverted the middle one, and gave it to an AND gate, and that was our Z, right? So it's really and then the clocks were connected to each other. So it's really a shift register, and it should be. Like, if you think about the question that we were trying to solve, we were really looking at a 3-bit, like a serial, basically array of bits that are coming in, and every time we shift the 3 bits that we actually are looking at by 1 bit. So that's what we're really doing with the shift register. So W is coming in from the left, and well, whatever goes at the, basically whatever was at the output of the third flip-flop is going to be thrown out after the next clock cycle, right? So we could have done this in an intuitive way, but again, similar to all the Carnot map problems that we solved in the past, that some of them were simple enough that we could solve them intuitively. Here is the same thing. For this example, we could have solved it intuitively, but then we might face, and we will face, you're going to see more examples here, that we will face problems that you can't really come up with any kind of intuitive design without this procedural way. So I'm going to continue solving the same example, but this time with a different kind of solution, and this is really the real solution that we are going to have. We're going to show that what we did up to now was really instructional, but was not really the most efficient way of solving that question. So if you think about it, the way we solved it, we said that we have 8 different states. Our state diagram had 8 different states from 0, 0, 0 all the way to 1, 1, 1. And the reason for that was, well, 101 has 3 bits, so let's go with 3-bit states. So with 3-bit state, we could have 8 different possible numbers, and then based on that, we kind of draw our state diagram. But if you think about it, we really didn't have 8 distinct states, right? What do I mean by that? Let's say that you're waiting for your friend again, right, at the airport, and people are coming out of the gate, and you're looking at them, and you know that you have to find the guy with eyeglasses who's coming after the guy with green jacket who's coming out after the guy with eyeglasses. So first you're really waiting for the first guy with eyeglasses. As long as people with green jackets are coming out, you don't care about them. It doesn't matter if the last 3 were green jackets or last 2 were green jackets. You need your first guy with eyeglasses, and then you become interested in who's coming after that and who's coming after that, right? So in this case, if I'm waiting for a 101, let's say I start with state A. And I define A as waiting for the first 1 to come in. Okay, so I should see this 1 first, and then this 0, and then this 1, right? So because we said things are moving this way. So as long as I'm in this state, my output is 0, and as long as I'm getting is W equal to 0, I'm going to stay in this state, right? So this state is kind of similar to our 0, 0, 0 state, where I haven't really seen any 1s yet, right? Now let's say that I do see a 1. W becomes 1. I go to state B. I'm going to define B as, let's write it up down here, seen the first 1. Okay, so now I've seen the first 1. I've seen the first guy with eyeglasses, and now I'm interested in if the next guy is gonna be basically a guy with green jacket. Let's say that happens. So I go to state C. So W equal to 0. State C is seen 1 and 0. Okay, and then let's say that we're very lucky, we see a W equal to 1 right after that. So our sequence is complete. I go to state D, my Z becomes equal to 1. For the rest of them, Z is equal to 0. And so state D, seen 1, 0, 1. Okay. Now, let's see what will happen if other inputs come in. So for state A, we talked about the 2 cases of W equal to 0 and W equal to 1. But state B, if I see a 0, it means that I have to go to state C where a 1, 0 has been detected, right? But if I see a 1, it's a 1, 1. It means that, well, I saw a guy with eyeglasses followed by another guy with eyeglasses. So it's not my pattern. But then do I go to reset mode? Do I go back to state A where I have to wait for the first guy with eyeglasses? Or I can think of it as, well, maybe this second guy with eyeglasses is my first one that I'm looking for, right? So basically, if I'm in the state B and I get another one, I would say it's almost like, let's say that this is the first one that I've seen, right? So I can actually say that I'm going to stay in state B. How about state C? So state C, I've seen a 1, 0. If I see another 1, I'm happy. I go to state D, everything is beautiful. But if I see a 0, so I'm at 1, 0 and I see a 0, right? So it becomes a 1, 0, 0, right? So where do I go from here? Well, there's no way that I can actually continue this and make this as a 1, 0, 1, right? Because if I add from this point, If I get a 0, I'm going to go to 0, 0, 0. If I get a 1, I'm going to go to 0, 0, 1, right? So this means that this is a dead end for me. The moment I get, if I'm in the state C and I've seen a 1, 0, and I get a 0, it's almost as if I'm going back to the state A and I have to wait for my first 1 to come in. So W is equal to 0. How about state D? So if I'm in the state D and I get a 0, so I've been in the state that I had the 1, 0, 1. Everything was good. Now I get another 0. It means that I throw out this one and I get the next 0 here, right? I go to a state 0, 1, 0. So now from this point, what do I need to actually get? Where do I go from here? Do I go back to 0, state A, or do I go back to a different state? If you think about it, at this point, if I get another 1 coming in, I'm going back to state D. It's almost like the last 2 bits that I've seen are a 1 and a 0. So if I get a 0, I go back to state C. And if I get a 1, well, I was in 1, 0, 1, and I get a 1, then it means that, well, I've thrown this out. It's almost like I don't have a 1, 0, but I do have a 1. The last bit that I have is a 1. So I've got my first 1. I could be hopeful that, well, after this, there's going to be a 0 and a 1. So it's almost like I've seen my first 1. So from this point, I go from here to state B. Okay. So using these analyses, you can see that we really didn't have 8 distinct states. Some of these states were kind of redundant from our perspective. They weren't really redundant, they were unique in their own way, but then from the perspective of detecting a 1, 0, 1, I don't care if the last 3 bits were 0, 0, 0, for example, or a 1, 0, 0, because I still have to wait for the first 1 to come in for both of them. So it's kind of like basically they're the same thing to me. I'm in the state of waiting for the first 1 to come in. And then state B would be, I've seen the first 1, I'm waiting for the 0 to come in after that. If I see another 1, then I'm going to say, I'm actually still in the same position because I've seen my first 1, I'm waiting for the next 0 to come in, right? So basically a 0, 0, 1 and a 0, 1, 1 are pretty much the same thing for me, right? So you can see that a lot of those 8 states could be actually merged into to 1 state, and then basically we can convert an 8-state system to a 4-state system. Okay. Now, if I want to actually draw the table, the rest of the process is going to be pretty much the same. But the beauty here is that because I have a 4-state system, I can call state A 0, 0, this one 0, 1, 1, 0, and 1, 1. And this way, I can actually have only 4 rows in my table. Everything is going to be much simpler. So I'm going to have just y1 and y0, and then here w equal to 0, w equal to 1 for y1 prime and y0 prime, y1 prime and y0 prime. And then my table is going to be 0, 0, 0, 1, 1, 0, and 1, 1. This is state A, this is state B, C, D, right? Now, if I'm in state A and I get a 0, this is the case. Therefore, I would stay at state A, so it's going to be 0, 0. If I get a 1, I go to state B, which is 0, 1. In state B, if I get a 0, I go to C, which is a 1, 0. And if I get a 1, I stay at state B, so I get I'm going to be 0, 1. Okay. So similarly, I'm going to fill this out. So for state C, I'm going to have 0, 0, and 1, 1, and 1, 0, and 0, 1. As for the output, well, I'm going to get a 1 when I'm in state D. So this is going to be the output. Okay, now how do I generate my Carnot maps? Well, similar idea as before. It's just that because I have only 2 bits for my state and 1 bit for my input, my Carnot map is going to be half the size. So I'm going to have y1, y0, and w here. And basically, so first I'm going to fill it with this column. So it's basically, I'm going to get 0, 1, so 0, 1, then, and then because I go to 1, 1, then 1, 0, it's going to be another 1, another 0. So 0, 1, 1, 0. And then for this is going to be 0, 0, 0, 1. Okay, so the Carnot map is going to give me this and this. So, and this is for y1 prime. So y1 prime is going to be equal to w bar y0 plus w y1 y0 bar. I can do the same thing for y0 prime. So this is going to be y1, y0, w 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1. And let's use orange. So I'm going to look at this. So this is 0, 0, 0, 0. So that's the first row. Nothing interesting there. And for the second row, it's all 1, 1, 1, 1. Great. So this one is actually quite easy and simple. So y0 prime is going to be simply w. Okay. Now that I have these two, I can actually draw the system. So my system is going to look like this. So I have my states are 2 bits. So I have a 2-bit states. So 2 flip-flops. The output of the flip-flops are going to be y0 and y1. So y1 and y0. I'm going to have clock. I'm not going to show it just, or maybe I should. Just trying to make this as clean as possible. So y0 and y1. So when do I get an output that is 1? Well, when both of them are 1. So just an AND gate. So Z here. And then with the input, I'm going to have y1 prime and y0 prime. And basically, so for y1 prime, I know that it is basically an OR gate of the 2 terms. So I'm going to need an OR gate. And then the OR gate is basically coming from 2 AND gates. So one AND gate is W bar or W Y1 Y0 bar. So say this is W Y1 and Y0 bar. So let's say I bring my Y1 here and then my Y0 bar from here. Put an inverter and that goes there. Okay, and then the other one is W bar Y0. So let's use a different color. So this is Y0, so I'm going to use it again. And W bar is like this. Okay, so now I made my Y1 bar. Now for Y0 bar, sorry, my Y1 prime. Y0 prime is simply W. So let's use red. So W could be connected to Y0 prime. Okay, so this is my circuit, and if you think about it, it has this shape that we thought it's going to have. So remember we said I'm going to have the combinational circuit, another combinational circuit, and then the array of flip-flops in the middle. Okay, So I hope that this was clear to you guys. I would say try to actually um, solve this for yourself. Try to do it yourself and try to understand fully how did we actually draw this state diagram, how did we move from state diagram to state table, and how did we make the diagram, right? If you had any questions, you can actually ask me during the office hours. Just email me that you want to talk during the office hours, and I would be happy to talk to you through video conference using Zoom and explain as much as you need. For the next lecture, I'm going to be starting, I'm going to solve a couple of more examples on this, right? So if you think that you've understood everything, you can get started and do this as a homework. Let's say that you want to detect, basically design a system that detects a 1101 or a 1011. So you want to actually have your flag up when either of these patterns are actually detected. So again, start with the state diagram, and then from there go to the state table, then to the Carnot maps, and then to the circuit. So this would be step 1, step 2, step 3, step 4. Okay, talk to you later.